Hello everyone, this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll be discussing about code converters. So, what do you mean by code converter and how to design various code converters? That means a combination logic circuit to convert one form of binary code into the other form. How to convert them, what is the procedure for designing them, and as an example, we will be discussing the designing of binary to Bcd code converter, Bcd to Xs3 code converter, Bcd to gray code converter, and gray code to Xs3 code converter. So first of all, what do you mean by code converter? So the code converters are used to convert one type of binary code to another form. So there are different types of binary codes like Bcd code, gray code, Xs3 code, and so on. So binary codes means what? It is nothing but grouping the binary information into some codes. It is nothing but binary code. So we have various types of binary codes like Bcd code, gray code, Xs3 code. And what is the necessity of binary codes? In order to make ease of transmission and in order to reduce the memory required or else storage required to store the data, binary data. If you can group them into bits, or if you can group the bits so that the memory we can form codes, then the memory required for storing them will be less, and even the transmission also requires less time. Instead of transmitting the binary data, if you could transmit the code, it requires less time. So that those are the advantages. So that is why we are going for the binary codes. So different codes are used for different types of digital applications. So we have so many types of binary codes, right? So each and every code can be applied in a specific application. So to get the required code from any type of code, the simple code conversion process is done with the help of combinational logic circuit. So here, first of all, if you have a binary Bcd code, so the Bcd code is nothing but binary coded decimal. So wherein the decimal digits, decimal digits are 0 to 9 will be coded into binary. To code this decimal digits into binary, it requires 4-bit binary code. So that code we are calling it as Bcd code. So Bcd code 0 to 9 numbers represent the equivalent binary numbers. That means the decimal numbers or its decimal digit 0 to 9 are represented in its equivalent binary number in a Bcd code. So for the number, and if a decimal number is having 2 digits, that means greater than 9. If a decimal number is greater than 9, that is for example 10, okay, or else 11, so which is having 2 digits. So we have decimal digits are 0 to 9. So greater than 9 or nothing but decimal numbers of 2 digits. For example, if I want to convert a decimal number into Bcd, so how can we convert them? So the LSB of decimal number is represented by its equivalent binary number, and also the MSB of a decimal number is also represented by their equivalent binary number. So as I told you that in order to convert a decimal digit 0 to 9 from binary 0 to 9 into binary, I require 4 bits. So that means the LSD, that is the least significant digit, should be replaced by its 4-bit binary equivalent, and also the most significant digit should be replaced by its 4-bit binary equivalent. So that is for example, let me write the Bcd code for decimal number 12. So where LSD is 1 and this is MSD and this is LSD. LSD is nothing but least significant digit and this is the most significant digit. So as I told you that MSD and LSD both should be replaced by, actually this is MSB. So this is LSB. Okay. So here each digit should be replaced by its 4-bit binary equivalent. So 2 can be represented as a 4-bit binary number as 0010, whereas 1 can be represented as 0001. So the MSB, which is most significant bit, is replaced by its 4-bit binary equivalent 0001, and 2 is replaced by 4-bit binary equivalent 0010. So as these zeros which are in the MSB position does not have any value, that is why I can remove this, and hence the BCD code for 12 can be given by 10010. Sorry, not double zero. No, it is double zero. 10010. So this is the BCD code for the given decimal number 12. So like that, whatever it may be the decimal number, how many digits it may have, simply we need to replace each decimal digit by its 4-bit binary equivalent. For example, if I consider a 3-bit binary number, 3-bit decimal number 359, and let us try to write down the BCD code for this one, replacing each digit with its 4-bit binary equivalent 00. The 4-bit binary equivalent for 3 is 0011, whereas 4-bit binary equivalent for 5 is 0101, and 9 is 1001. So again I can remove this. So the BCD code for 359, which is a decimal number, is given by this. This is the BCD code for the given decimal number 359. So like that, we can find out the BCD code for any number, any decimal number of any digit, simply by replacing each digit by its 4-bit binary equivalent. Okay. So now I want to design a BCD binary to BCD code converter. So for that, first of all, binary to BCD code converter. So I am taking a 4-bit binary number, and I want to find out or else I want to design a circuit such that it converts any 4-bit binary number into its equivalent BCD number. So here, now, as we have 4-bit binary number, so what are the possible combinations of input we may have? 2 to the power of 4, that is 16. So which will be varying from 0000 to 1111. So this is 0 decimal number 0, and this is decimal number 15. So these are the all possible combinations for the 4-bit binary number, that is 0 to 15, and we need to write on the equivalent BCD code. Actually, we have some steps. What are the steps here? And whenever we are designing a combinational circuit, we have to follow some few steps. First, we need to identify the number of inputs and outputs. And the second step is label the inputs and outputs. Label the inputs and outputs with some literals. Okay, literals are also called as variables. Okay, after that, construct the truth table. Construct the truth table based on the logic you want to implement. Construct the truth table. Okay, so these are the steps you need to keep in mind whenever you are designing a combinational logic circuit. Once the truth table is constructed, now we have to draw the K-map for each output to get simplified Boolean expression in terms of input variables. To get simplified Boolean function, in terms of input variables. Once the Boolean functions are available, then what we can do, using the logic gates, that is a basic logic gates and or invert, you can implement the logic circuit, and or invert, implement the logic circuit. So these are the steps that we need to keep in mind. So this is nothing but the a circuit that is going to perform a specified task. Okay, so like that you can implement any combination logic circuit with these 4 steps. So now I have identified I want to design a 4-bit binary to BCD code converter. So what is the maximum value of a 4-bit binary number? 15. So how can I represent this 15 in BCD? 15 can be represented in BCD as 001, 0101, right? So that means these zeros can be neglected. So that means the BCD code for 15, which is given by 10101. So what is the maximum number of bits in the BCD code to represent the maximum value of 4-bit binary number? 5-bit. So that is how we can decide the number of outputs. So what is the number of output? It is a 5-bit output. So the number of inputs are 4 and the number of outputs are 5, and the inputs I am representing, as it is a binary number, I want to represent the input variables as B3, B2, B1 and B0, whereas the output is BCD, which is a binary coded decimal. So I want to represent whatever the variable you want to assign, you can assign. So I am giving the variables for the outputs as D4, D3, D2, D1, D0, because the resulting BCD code must have 5 bits. So that is why I am taking 5 variables as the output variables. So now I am writing the input combination, all the possible input combinations here, starting from 0000 to 1111. Now coming to the BCD code, the 0 can be represented. So this is a decimal number 0. The 0 can be represented in BCD code as 0, all zeros here, and 1 is 0001. So in order to represent 1, it requires only 4 bits. So, but here as I am taking 5-bit output, so extra by 1 more bit I am adding, that is 00001. And next 2 is 00010, and 3 and up to 9 it is equivalent to the binary code, right? So 01001. Now coming to the 10 here. 10 in binary is represented as 1010, whereas in BCD 1 is represented as 0001 and 0 is represented as 0000. So that is why we got the BCD code for 10 as 10000. Next 11, 1011, whereas 11 can be represented as 10001. Next 12, it is 10010, and 13 it is 10011, and 14 10100, and 15 10101. So these are the BCD codes for the decimal numbers 0 to 15 and their respective binary codes. So what is our aim? I want to design a circuit in order to convert a given 4-bit binary code into BCD code. So now this is the truth table. So up to the third step has completed. Now what we need to do? We need to get the Boolean expression, for simplified Boolean expression for all the outputs D4, D3, D2, D1 and D. So here if you observe this, D4 is 1 for, so I want to get the Boolean function in SOP form. So in that case, what should we consider? We should consider the input combinations for which the D4 output is equal to 1. So the D4 output is becoming 1 for the combinations, that is 10, 11, 12, 13, 14, 15. Okay. So that is why I can write down the Boolean function for the 5 outputs, that are D4 is equals to summation M of 10, 11, 12, 13, 14, 15, because I want to get the Boolean function in simplified SOP form. So that is why I am considering only the combinations for which the function output, that is D4 output, is equals to 1. So this is the SOP form of Boolean function for D4. And similarly, if you look at the D3, it is becoming 1 for 8, 9, only 8, 9. So that is why the output is D3 is given by summation M of 8, 9. Now coming to the D2. So D2 is 1 for 4, 5, 6, 7 and next 14, 15. 4, 5, 6, 7, next 14, 15. And similar, so D2 is given by 4, 5, 4, 5, 6, 7, 14, 15. Similarly, D1 is 1 for the minterms, that is the possible combinations 2, 3, 6, 7, 12, 13. So for all these input combination, D1 output is becoming 1. And D0 output is becoming 1 for the combinations 1, 3, or else for the minterms 1, 3, 5, 7, 9, 11, 13, 15. So now what is my aim? I want to get the simplified Boolean function for this D4, D3, D2, D1 and D0. For that, I need to construct a K-map. So how many variable K-map we need to construct? The number of variables should be equal to the number of input variables. So how many input variables we have? 4 input variables. So that is why I have to take a 4 variable K-map for deriving the simplified Boolean functions for all the all the 5 outputs of binary to BCD code converter. So now first let us let us draw the K-map individually for each and every output. So the first K-map is D4. So here it is a 4 variable K-map I am taking. So the input variables we have represented as B3, B2, B1, B0. As you all know that this order should be same as the order which we have followed in the truth table. So B3, B2, B1, B0. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. This is a 4 variable K-map. Right? Now D4 function is becoming 1 for the minterms of 10, 11, 12, 13, 14, 15. So this is, if you consider this as 0, 1, 3, 2, this is 4, 5, 7, 6, and this is 8, 9, 10, 11, and this one is 12, 13, sorry, this is 11 and this is 10, and 15, 14, right? So now D4 is becoming 1 for 10, 11, 12, 13, 14, 15. This is 10, 11, 12, 13, 14, 15. And for all the remaining minterms, the function output is considered to be 0. So these are marked. So I want to get the Boolean function in SOP form. So for that, I should only group the cells which are marked with 1. If you want to get the Boolean function in SOP PYS form, you have to group all the cells, adjacent cells which are marked with 0. So now I am grouping only the cells which are marked with 1, where the cells marked with 0 are left. So now I can form, by looking at this, these 6 cells are mapped with 1s. So I could not form an octet here because only 6 cells are mapped with 1. So the next higher group that we can form is quad. That is a group of 4 cells. So here I can form a quad with this row such that all these 4 ones are covered and these 4 adjacent cells are grouped together because these ones to be covered here. So now if you write down the prime implicant for this one, so if you consider this row, B1 and B0 value is varying, eliminate B1 and B0, whereas B3 and B2 value are common, which are equals to 1. So B3, B2. So B3, B2. Now coming to this one, this quad is formed by these 2 rows and these 2 columns. For these 2 rows, B3 is common, whereas B2 is varying, eliminate B2, and B3 is 1, so that is why take it in the form of true form. Now consider these 2 columns, B1 is 1, B0 is 0. So as B1 is 1, consider B1, B0 is varying, eliminate. So this is the equation for D4, which is B3, B2 plus B3, B1. Now similarly for D2, sorry, not for D2, D3. So for D3, the D3 function is becoming 1 only for the minterms 8 and 9. So 8 and 9 are marked with 1. Only a pair can be formed because only 2 cells are marked with 1 and remaining all the cells are marked with 0. So I can group only these 2 because these 2 are adjacent. So now if I write the prime implicant for this, if I can write the prime implicant for this one, so as this is formed by this row, so which is having common value B3 as 1 and B2 as 0. So B3, B2 complement, whereas for these 2 columns, B1 value is common, which is 0, whereas B0 value is varying, eliminate B0, so B1 complement. So B3, B2 complement, B1 complement, right? Similarly, you can find out the equation for D2, where D2 function is becoming equal to 1 for 4, 5, 6, 7, 14, 15. So 4, 5, 6, 7, 14, 15. So now I can form 2 pairs here, 2 quads here again. So this quad can be written as B3 bar B2 because B3 value is 0, B2 value is 1. Whereas B1, B0 is varying for all these 4 cells, eliminate B1, B0. And for this one, these 2 are the rows here. So B3 value is varying, eliminate B3, where B2 is common, B2, and B1 value is also common, so B. So B2, B1, B3 bar, B2. So this is D2. Similarly, D1 is 1 for 2, 3, 6, 7, 12, 13. 2, 3, this is 2, 3, this one. 2, 3, this is 2, 3, and this is 6, 7, and this one is 12, 13, right? So I can form a quad with this 4 cells, and I can form a pair with these 2 cells, and this one can be represented by B3 bar B1, and this pair can be represented by B3 B2 B1 bar. Okay, and now coming to this D naught, 1 3 5 7 9 11 13 15 1 3. So this is 1 3 5 7 9 11 14 13 15. So I can form an octet here. If I could form an octet, so this B3 B2 values are varying for all these 8 cells, so eliminate B3 B2. Whereas if you consider these 2 columns, B2 B1 value is varying, eliminate B1, whereas B0 value is common, so D0 is equals to B0. So these are all the equations. So now after getting the equations, so we need to implement that using logic gates. So this is the logic circuit for a binary to BCD code converter, which is constructed with the help of minimized Boolean functions for all the 5 outputs D4, D3, D2, D1, D0. So we are taking 4 inputs here, B3, B2, B1, B0, and their complements. So if you look at these expressions here, none of these expression is required B0 complement. So that is why I am not taking B0 complement. So here this is D0, where D0 is equals to B0. Whereas G1, what is G1 here? First AND gate, this is B3 and this one is B2 and this one is B1 complement. So B3, B2, B1 complement. Next plus, this one is what? B3 complement and this one is B1. So B3 complement plus B1. Sorry, B3 complement into B1. B3 complement into B1. Now coming to this one. So this is B3 complement and this one is B2. Okay. So that is B3 complement B2 and this is B2 B1 plus B2 B1. And what about this one? I'm taking the inputs here. This is B3. Okay. B3 into and this input is what? B2 complement. Next, this input is B1 complement. B3, B2 complement, B1 complement. And coming to this one, this is B3, B2 plus this one is B3, this is B1. B3, B2, B3, B1. B3, B2 plus B3, B1. So this is the implementation of this binary to BCD code converter using basic logic gates. So this is how you can implement a binary to BCD code converter. Now let us look at the BCD to Xs3 code converter. So you know Xs3 code, how to get the Xs3 code. So we have to add 3 to the number so that you can find out the BCD code. So Xs3 code. So as you all know that BCD code means even it is a 4-bit number or else it is a 4-bit code, but only we have 0002 1001 as valid codes, whereas the remaining codes with a 4-bit binary code, there are 16 possible combination, but I am using only 10. That those are from 00002 1001, whereas the remaining combination 10102 1111 are considered as don't care conditions. That means for which the output is unspecified. Okay, so that is the binary to this is a BCD code. So I want to convert a BCD into Xs3 code. So what is the maximum possible value of a BCD code? 9. 9 plus 3 is 12. 12 in a binary can be represented as 1100. That means in order to get the Xs3 code for the maximum possible output is again having a 4-bit. So that means in order to convert a BCD into Xs3 code, the number of bits, input bits are 4 as well as the number of output bits are also 4. Okay. So now the thing you have to remember is we are considering the input combinations as 0 to 9, whereas the remaining combinations are considered to be unspecified, where the output cannot be specified and hence it is considered to be don't care. Okay. So now let us write down the truth table for this one. This is a truth table where the BCD code is considered to be input. As I told you that in order to represent 0 to 9, I require 4-bit binary number. So this is the 4-bit input here. Okay, and these are the inputs and represented with D3, D2, D1, D0. And Xs3 code, as I told you that the maximum possible value is also can be converted into Xs3 code with the help of 4 bits only. So that is why my output is also having only 4 bits, which are represented as E3, E2, E1 and E0. So here these are the decimal equivalents for the BCD codes given here. So 0000. We are writing the listing the BCD codes here 00002 1001 and the respective Xs3 code. So what is the Xs3 code for 0? So 0 plus 3 is equals to 3 and the binary equivalent for 3 can be written as 0011. So this is the Xs3 code for decimal digit 0. Now 1 plus 3 is 4. So where 4 in binary can be represented as 0100. 2 plus 3 5 0101 and 3 plus 3 6 0110. 4 plus 3 7 0111. Next 5 plus 3 8 1000. Next 6 plus 3 9 1001. 7 plus 3 10 1010. 8 plus 3 11 1011. 9 plus 3 12 1100. So these are the respective Xs3 code for the BCD codes 0 to 9. Now what I should do? I want to derive the simplified Boolean expressions for this E3, E2, E1, E0. Now let us consider E3 is becoming 1 for summation M of. So for which combinations E3 is becoming 1? 5, 6, 7, 8, 9. So 5, 6, 7, 8, 9. Whereas it also includes some don't care conditions. What are the don't care conditions? 10, 11, 12, 13, 14, 15. These are the don't care conditions. Similarly, E2. E2 is 1 for 1, 2, 3, 4. So summation M of 1, 2, 3, 4 and also 9 plus again the don't care combinations are same. Now coming to the, because we are not specifying the output for the combination 10 to 15. So even though the input is a 4-bit, but I am not using this. So that is why we are considering these combinations as don't care. Now E1 can be considered as summation M of 0 and this is 3 and this one is 4, 0, 3, 4, 7, 8 plus don't care conditions. Okay. Next E0 can be considered as summation M of 0 to 4. Okay. 0 to 4, 6 and then 8 plus don't care conditions are common for all the 4 outputs. Okay. So now by using this, we need to draw the K-map and we need to get the simplified Boolean expression. So how many variable K-map is required? 4 variable K-map. So these are the 4 variable K-map for E3. So as I told you that 10, 11, 12, 13, 14, 15 are marked with don't care. 10, 11, 12, 13, 14, 15 marked with don't care. Whereas E3 is 1 for 5, 6, 7, 8, 9. So 5, 6, 7, 8, 9. So here by looking at this, whenever we have don't care conditions, I can use them if I could form higher order groups. So I could form an octet such that these two ones are covered by including these don't care. So that is why an octet was formed. And similarly, no other octets are possible here. I can form an octet, I can form a quad here and I can form a quad here. So like that, we have 3 groups here and the octet can be represented as D1, D0 are varying for this octet, eliminate D1, D0. And similarly, D2 is also varying, eliminate D2, only D3. And coming to this quad, second and third row are having D2 value as common, so D2, whereas third and fourth column, so D1 value is common, so D1, D2, D1. And coming to this one, so here D2 value is common again, whereas D1 value is varying, eliminate, so D0, so it is D0, right? So this is the equation D3 plus D0, D2 D0 plus D2 D1. So this is the equation for E3. And similarly for E2, so again we need to mark 10, 11, 12, 13, 14, 15 as don't cares. These are the don't cares. And now coming to E2, this is becoming 1 for the midterms 1, 2, 3, 4, 9. So 1, 2, 3, 4 and 9. So now I can form, I can form quad with this 2, and again only this one is left. So if I could use this don't cares and this one, again I could form a quad here. So I could not form any quad with such that this one is covered because no other adjacent cells are there. So I could just only form a pair with this. So now this quad can be represented as first row and last row. First row and last row, D3 value is varying, eliminate D3, whereas D2 value is common, D2 complement. And now coming to this one, this D1 value is common, so D1, D2 complement D1. Now coming to this quad, so here again D2 complement, and coming to look at these first, second and third column, so D1 value is varying, eliminate D1, whereas D0 is common, so D0. Okay, now coming to this pair here, so here if you consider this two rows, D2 value is common, D2, whereas D1 and D0 are common, so D1 complement, D0 complement. D2, D1 complement, D0 complement, D2 complement, D0, D2 complement, D1. So this is the function. Similarly for E1, so again 10, 11, 12, 13, 14, 15 are don't cares, and E1 is becoming 1 for 0, 3, 4, 7, 8. 0, 3, 4, 7 and 8. So I could form two quads here and their respective prime implicants this. Okay, so I could eliminate D3, D2 for both of the quads here. So now I could consider only this value, so which is nothing but D1 complement, D0 complement, and this one is D1, D0. And now coming to E0, so again 10, 11, 12, 13, 14, 15 don't cares, and coming to this 0, 2, 4, 6, 8. 0, 2, 4, 6 and 8. So I could form again two more quads here. So not quads here. These are the rows, these are the columns. These two columns are adjacent to each other. So I could form an octet. So if I could form an octet here, so D3, D2 values are varying, eliminate D3, D2. For these two columns, D1 value is also varying, eliminate D1, whereas D0 value is common, which is equals to D0 complement. So based on that, this is a logic circuit. So here E0 is equals to D0 complement and E1 is equals to D1 complement, D0 complement. Okay, D1 complement, D0 complement plus this one D2 complement and D0 plus D2 complement D0. Okay, so this is the equation for E1. And coming to E2, so here this is D3, D1 complement, D0 complement, and this one is D2, and this one is D0. Okay, D2, D0. And coming to this one, this is D2 complement, D1. So finally you will get D3, D1 complement, D0 complement plus D2, D1, D2, D0. D2, D0 plus this one is D2, D1. D2 complement, D1. Okay. So this is the equation for E3. And E3 it is D2. Next this one is D0 complement. And this one D2. And this is D1. D2, D0 complement plus D2, D1. So this is the implementation of BCD to Xs3 code converter. Now the next one is BCD to gray code converter. And you know the basic principle for converting a given binary number into gray code. How to convert a given binary number into gray code. So this is the principle. Just we have a look at this one. So the gray code, MSB of gray code and MSB of binary code are equal. So now the next bit of gray code can be formed by exclusive ORing the B3 and B2. So which will give you G2. And the exclusive OR of B2, B1 will give you G1. And the exclusive OR of these two bits will give you G0. So this is the gray code. So as we have BCD to gray code converter. So what is the input? BCD code. So again BCD code means 0 to 9. The remaining 10 to 15 are considered to be don't care. So the input is having 4 bits, whereas gray code. So gray code and binary code will have equal number of bits. So the gray code is output is also 4 bits. So 4-bit input and 4-bit output. And while writing the inputs, we need to consider only 0 to 9 because it is a BCD code. So where the remaining combinations are considered to be don't care or unspecified. So this is the truth table here. And the inputs are represented with D3, D2, D1, D0. Whereas the gray code equivalent, which is the output, is represented as G3, G2, G1, G0. So now I'm writing the gray code for this. These are the BCD codes 0 to 9, 000 to 1001. Now the respective gray codes here. So the MSB is same and the remaining bits are formed by this principle. So now 0, 0 XOR 0, 0, 0 XOR 0, 0, 0 XOR 1, 1. Now coming to this, MSB is 0, 0 XOR 0 is 0, 0 XOR 1, 1, 1 XOR 0, 1. Now coming to this one, MSB is 0 and 0 XOR 0, 0, 0 XOR 1, 0 XOR 1, 1, 1 XOR 1 again, 0. Okay. Now coming to this one, MSB is 0 and this is 0 XOR 1 is 1. So you all know that XOR operation A XOR B. So when both the inputs are same, either 1 or 0, the output of the XOR gate is 0. When both the inputs are different, then only the output of the XOR gate is equals to 1. So based on this principle, we are writing the gray code here. So now 0 XOR 1, 1, 1 XOR 0, 1, 0 XOR 0, 0. Now coming to this one, MSB 0, 0 XOR 1, 1, 1 XOR 0, 1, 0 XOR 1, 1. So next, this one, 0 XOR 1, 1, 1 XOR 1, 0, 1 XOR 0, 1. Next, 0 is MSB, 0 XOR 1, 1, 1 XOR 1, 0, 1 XOR 1, 0. Now similarly, these are the equivalent gray codes. Now we need to find out the simplified Boolean expression for all this. So first of all, G3 is becoming 1 for summation M of this, what is a combination? 8, 9. And we do have don't care conditions. What are the don't care condition? 0, that is 10, 11, 12, 13, 14, 15. Similarly, G2 is becoming 1 for 4, this is 5, 4, 5, 6, 7, 8, 9. So summation M of 4, 5, 6, 7, 8, 9. Right? Now coming to G1 is becoming 1 for 2, 3, 4, 5. 2, 3, 4, 5. Okay. And still we have don't cares. And G0 is becoming 1 for summation M of 0, 1. Sorry, not 0, 1. It is 1, 2. It is 1, 2 and then 5, 6, 9. 1, 2, 5, 6, 9. So this is G. So now we are drawing the K-maps here. This is a G3. So we have seen that don't cares are 10, 11, 12, 13, 15 and G3 is becoming 1 for 8 and 9. So G3 is becoming 1 for 8, 9. Remaining all are don't care. So I could form a quad here, octet here. So where octet, the prime implicant for this octet is D3. So G3 is equals to D3. Now coming to G2. So G2 is becoming 1 for 4, 5, 6, 7, 8, 9. So 4, 5, 6, 7, 8, 9. The remaining all are don't cares here. So I could form 2 octets here by including the don't cares. So this octet can become D2 because D3 is varying, eliminate D3. D1, D0 are also varying, eliminate D0. Only D2 is common for all these 8 cells, which is equals to 1. So D2. Now coming to this one. So again D1 and D0 values are varying for all these 8 cells, eliminate them. And D2 value is varying, eliminate D2, whereas D3 is common. So D2 plus D3. Now coming to G1. G1 is given by G1 is 1 for 2, 3, 4, 5. So 2, 3, 4, 5. So 2, 3, 4, 5. remaining all don't care. So I could form an octet here, quad here, and I could form a quad here. 2 quads are possible here. Now coming to this quad, so D3 value varying, eliminate D3, whereas D2 is common, so take it in the true form. Whereas D1 value is common, consider D1 which is equals to 0, so take it in the complement form. D0 is varying, eliminate D0. Now coming to this first and last rows, D2 is common, so D2 complement, and D3 is D3 is varying, eliminate D3. Now coming to this one, D1 is common, so D1. So D2 D1 complement plus D2 complement D1, or else we can also write this one as D2 XOR D1. Right? Now coming to G0, G0 can be written by, so here G0 is becoming 1 for 1, 2, 5, 6, 9. 1, 2, 5, 6, 9. So 1, 2, 5, 6, 9. 1, 2, 5, 6, 9. And the remaining don't care. So I could form 2 octets here. Sorry, 2 quads here. And this can be written as D1 D0 complement. And this one I can write it as D1. So this can be written as D1 complement D0. And this can be written as D1 D0 complement. So I can write it as D1 XOR D0. Okay. So finally the Boolean function for this one is this one. G3 is equals to B3. So D3. And now coming to the G2. G2 is equals to D2 plus D3. So D2 plus D3. This is D2 plus D3. Whereas this is D2 D1 complement. And this one is D2 complement D1. So this is D2 complement D1 plus D1 complement D2. And this one I could write it as, this one as D0 D1 complement, and this one as D1 D0 complement. So D0 D1 complement plus D1 D0 complement. So this is the implementation of that Boolean function. Now the last one, gray code to Xs3 code. So we all know that gray code to Xs3 code. So first of all, actually my input is a gray code, and whereas the output is Xs3 code, right? So here I'm writing a gray code. I want to implement a 4-bit binary gray code to Xs3 code. So before getting the gray code, so I just want to write on the binary code and then gray code. But I have to consider only for getting the gray code, I'm writing this binary. It is not needed actually. If you are able to write down the gray code as on your own, you can write on the gray code. Okay. So now here, this is the binary code and the respective gray codes here. So from 0 to 12. Okay. So the next here, that is 0000, and the binary code for 0001 is binary code, and the gray code for this one is the same thing. Whereas the binary code is 0010, gray code is this one and this one. So as the gray code is representing binary equivalent of 0, so I could write this one as 3. Whereas 1 plus 3 is 4, so 0100. And next 2 plus 3 is 5. This is the Xs3 code, right? So 3 plus 3 is 6, 00110. Next 4 plus 3 is 7. This one. So that means we are writing the gray code, binary code for the respective gray code and Xs3 code for the respective binary code. So this is considered to be my input and this is considered to be my output. Okay. So now we get here again. So why I am considering only 12? Because after 12, so that is 13. 13 plus 3 is 16. 13 plus 3 is 16. So in order to represent 16, how many bits we require here? I require 5 bits. But I am designing only a 4-bit gray code to Xs3 code. So that is what these are. These values, that is 13, 14, 15 are considered to be unspecified. Unspecified because we are designing gray code to Xs3 code. As I told you that in an Xs3 code and gray code, the number of bits must be equal. So that is why I am considering only 4-bit Xs3 code. So in that case, only I have to consider 0 to 12, whereas 13, 14, 15 can be considered as unspecified conditions. So that is why I have marked that 13, sorry. Okay, sorry, not that, actually. So here, if you could see this, so we have unspecified combinations. What are the unspecified combinations? 0 is there, 1 is there, 3, 2, and 6, 7, 5, okay, 5, and 4 is there, 12, 11. Only I could not see this 8, 9, 8, 9, 10 is also there. 8, 9, 11 are not present in the input code. So that is why 8, 9, 11 are considered to be don't cares. 8, 9, 11 are considered to be don't cares. We could not find 100 in the gray code and 1001 in the gray code also. And also 1011 also not seen in this gray code. So that is why I am not considering these. I am considering these as don't care conditions. So that is why 8, 9, 11 or the don't cares, and this is the output for Xs3 code, for which the combinations, that is this E3 output is 1 for 4, 5, 7, and this one is 12, 13, 15. 12, 13, 15. So that is why I could write down the equation for E3 as this. And coming to E2, by considering 8, 9, 11 as don't cares, okay, and the remaining for which combinations the function output is becoming 1. That is 1, 2, 3. Next, this is 6. Okay. So E2 is becoming 1 for 1, 2, 3, 6. Next, 10. And then this is 13, 13, 13, 15, 14, 15. So for these combinations, it is becoming 1. So I could form 2 quads and 2 quads, and even I can form one more quad also with this. So we can also form a quad with these two also. Okay, so that I could simplify this expression. Okay, so like that we can get the simplified expression. So for E1, this is a simplified expression. For E0, this is a simplified expression. And after getting the simplified expressions, so we can form a Boolean function. So here no other cells are adjacent to each other. So no two cells are adjacent to each other. Even though we don't have any adjacent cells to each other. So that is why I could form an expression by taking them as usual, and also by simplifying them by forming groups. So here now that means by algebraic expressions we can simplify them, and we can get the simplified Boolean expressions as G1 XOR G0 XNOR, G3 XNOR G2, G1 XOR G0, G3 XOR G2. You just try it. So just take all the prime implicant as it is, and then try to get the simplified expression as this one. Okay. So now the thing is we need to implement that using logic gates. So this is the implementation of all the Boolean function which we have got from the K-map. So these are the E0, E3, E2, E0, E1, E2, E3 Boolean functions, and that is the implementation using logic gates. So like that you can implement any combination logic circuit which can convert one form of code into other. So you can try for binary to gray code, binary to gray code converter. So you can try this. If you have any doubts, you can post it in the comment section. Binary to gray code converter, and also gray to binary converter. So as you all know that 4-bit binary I am taking. So how to convert a 4-bit binary number into gray code, just now I have discussed. Now if you have a gray code, 4-bit gray code, G3, G2, G1, G0. How to get the binary code? So first again, the MSB is same. So now the XOR of this and this, one will give you B2, and the XOR of these two will give you B1. We are performing XOR operation. XOR of these two will give you B0. Okay. So this is what, by using this, first write down the gray code and then get the equivalent binary code for the respective gray code. That means again we have 4-bit binary number and 4-bit gray code, and also will have the 4-bit binary number. So in both the cases, this is first case and second case, input variables are 4 and the output variables are also 4. First form the truth table and then get the simplified Boolean expression for all the outputs and then implement them using the same procedure. Okay, so this is what the code converters. I hope it is clear to you. So now you are able to convert any form of code into any, you are able to design a combination logic circuit such that you can convert any form of code into the other form of code. So I hope it is clear to you all. If you have any doubts, you can post it in the comment section. That's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.